Log on, tune in, find out. Another good idea from Cambridge.
One can use nonlinear Fourier transform to produce images from EIT measured data. Let me mention first that I represent the Finnish Center of Excellence in Inverse Problems Research that has the goal of filling whole of Finland with inverse problems research groups. Starting next year, we'll have one more in Jyväskylä here, like Mikko Salo got the professorship there, so we are expanding. Okay, this work I'm talking about is a joint work with David Isaacson from RPI, Kim Knudsen from Denmark, he's in Copenhagen, Matti Lassas from my department in Helsinki, John Newell from RPI, and Jennifer Mueller from Colorado. And my talk is divided today in these parts. First, I describe what this electrical impedance tomography is. Then let's see, just in general terms, what needs to be done in the solution of ill-posed nonlinear problems. It's called regularization, so let's see what it is. Then I'll show what is the D-bar method. This is according to Nachman's proof for the two-dimensional inverse conductivity problem published in 1996. And then I'll show what extra steps are needed to make it really regularized and work in practice. And the step actually is kind of a nonlinear low-pass filtering. And then I'll show you some pictures and tell you how these things are computed in practice. So electrical impedance tomography is an imaging method where an unknown target, for example the human body, is probed with electrical currents using, for example, electrodes like this. Then the resulting voltages are measured. The measurement is done again and again with different current patterns, and from all of this measurement data one wants to see the distribution of electrical conductivity inside the target. In the case of medical imaging, we would see what is inside the patient. And let me advertise the results of David Isaacson's group quickly to show what is, in my view, the most advanced application of EIT, namely helping X-ray mammography to find breast cancer. So this is a mammography device, X-ray based, so there's an X-ray source up here, the breast is compressed here in between these plates, and then an X-ray image is taken. Actually, this machine is capable of taking some limited angle tomography measurement with X-rays with some angular displacement. Here they have built in Boston, in Massachusetts General Hospital, they built these radiolucent electrodes so they can probe the breast also with electricity during the same compression that is used for the X-rays. And they do a sweep over some frequencies and want to complement these. These are slices through the limited angle tomography results. And now the question is, is there cancer or not? And as you may know, mammography is a really difficult topic. I mean, radiologists still make mistakes because the cancer and healthy tissue have roughly the same attenuation for X-rays. So cancer is not a white spot or a dark spot. It's a matter of very intricate textures and stuff like that. So is this cancer? Is this? It takes really a long education of radiologists to answer these questions, at least sometimes correctly. Now, if we combine this with frequency sweep EIT, we can see that there is no cancer, and here we have some malignant tumors. And as you see, this is not so high resolution spatially, but the contrast resolution is high. Namely, the conductivity in cancer is 4 times more than conductivity in healthy tissue. So that's why combining the high spatial resolution of X-rays and high contrast resolution of EIT can really help in finding breast cancer. Okay, today my main topic is a simulated chest image. So I'm thinking about this arrangement, and of course the current is flowing actually in a 3-dimensional fashion inside, but for some reason still, even assuming that it's a 2-dimensional measurement, gives usually quite useful pictures. So this is kind of what I have in mind in today's talk, and the mathematical setting is the two-dimensional version of Calderon's inverse conductivity problem. Now Calderon, who was an electrical engineer by training, was all his life very interested in applications of electrical measurements and their interpretation. And in the year 1980 he published an important paper where he laid the mathematical foundations of the inverse conductivity problem. So here the idea is that, no, in this talk I will use omega. Omega will be the unit disk, and inside the unit disk we have this conductivity function sigma, which is strictly positive, so it's bounded away from zero, and also bounded from above. And now Calderon asked, is the conductivity sigma uniquely determined by the Dirichlet-Neumann map lambda sigma? And if it is, how to compute sigma from the knowledge of the Dirichlet-Neumann map? So here, see, this is like the voltage to current map, in the sense that here we apply a voltage F around the boundary. Then inside, according to Maxwell's equations, we have here, this is the current vector field inside, and the divergence of the current field vanishes, meaning that there are no sources or sinks of current inside the domain. So we end up with this elliptic conductivity equation, and we look at this Dirichlet problem, solve this in H1 Sobolev space, and then take the normal derivative. So this object, this linear map, is the model of all possible static electrical measurements at the boundary. And let me mention that the problem of finding sigma from lambda sigma is a nonlinear and very ill-posed inverse problem. Even quite big differences in two conductivities may result in very small difference in the Dirichlet-Neumann map. And the mapping from sigma to lambda sigma is nonlinear, although lambda sigma itself is a linear operator. This is a quick overview of what kind of things people have suggested as numerical methods for solving the inverse conductivity problem or electrical impedance tomography. There are many approaches, and today I will be concentrating on these nonlinear direct methods, so direct as opposed to iterative. We are not iterating in the conductivity space. In these methods we are using a nonlinear Fourier transform, as we will see. Let's take a look at the history of these so-called D-bar methods. The story, of course, started with Calderon's paper. So this column here is the theoretical column. These are works dealing with the infinite precision data, that is the Dirichlet-Neumann map. It started with Calderon, then there was a groundbreaking paper by Sylvester and Ullmann, which is in dimensions 3 and higher, where they introduced the use of so-called complex geometric optics solutions. The two-dimensional story starts from Nachmann's breakthrough paper in '96. Later, the story goes that the requirement of smoothness in the conductivity was reduced step by step until Kari Astala and Lassi Päivärinta showed that actually the Dirichlet-Neumann map uniquely determines even L-infinity conductivities. This is the history of the numerical side, the history of implementing these complex geometrical optics-based methods. The first one is this one, based on Nachmann's work, and I think this Nachmann's proof, algorithms based on Nachmann's proof are the most advanced at this point, including this one giving a regularization analysis, which I'm talking about today. But there are also this Brown and Ullmann method has been implemented, and also Astala and Päivärinta method. But regularization analysis for those are still to be published. So that's why I'm concentrating on this one today. So let's see, what is this regularization? Of course, for some people in this audience it's quite clear, but let me still show the framework. So this is the way to think about inverse problems, linear or nonlinear. We have a model space X where the unknown object lives, which we measure indirectly and want to recover. And this is the so-called forward map F that takes the object to its measurement. In the case of EIT, it's a conductivity sigma, which is mapped to the Dirichlet-Neumann map lambda sigma. The forward map is typically defined only on some subset of the model space X. So I call this domain F, is marked by this black curve here. On this side, this curve here is the image of the domain of the forward map. So this is the range of the forward map. And I draw it in this curved manner because the structure of this set is really unknown in many cases. For example, in electrical impedance tomography, we don't know which operators in the data space actually are the Dirichlet-Neumann maps of some conductivity. So this is not, there is no characterization. So that's why this is just now an abstract set. And now what we measure in practice is something which is at most delta away from the infinite precision measurement. So this is what we are given in practice. Some kind of approximation to the ideal data, and from this one we should recover the conductivity approximately. And what makes it difficult is that in ill-posed problems, the forward map does not have a continuous inverse, not even when restricted to the range. This is like Adamar's ill-posedness. So what needs to be done is to construct a family of regularization mappings. So these are continuous maps. These gamma alpha are continuous maps from Y to X. So from the full space Y to space X, parameterized by alpha, which is a so-called regularization parameter. It's a real number between positive real number. And these gamma alpha maps, so they should be continuous from the data space to the model space, and they should satisfy some conditions. So first of all, if we had the infinite precision data, applying our regularization strategy should give us the perfect reconstruction in the limit when the regularization parameter goes to 0 for a fixed conductivity. Then when we work with really the noisy data, so this one, so what happens when we apply our regularization method to noisy data? First of all, we should specify how to choose alpha as function of the noise level. So we think we know the noise level. Typically, it can be calibrated from the measurement equipment. So there has to be a choice like this, that alpha goes to 0 asymptotically when the noise goes to 0. And then let's see what this means. So this is supremum over some maps. So supremum is taken over all data that is in the delta disk centered at the infinite precision data. And we look at these numbers. So this is the error in the reconstruction. This is the reconstructed quantity for a given alpha. We subtract it from sigma and measure the difference in the X norm. So this reconstruction error here should go to 0 as asymptotically as the noise level goes to 0.
Sorry, when you say the X norm, what is the X norm? The Orman space X for which norm?
In the case of EIT, it will be L infinity norm. But generally, it depends what is the choice of the data space. Why I will define in a minute. It's a space of linear bounded operators in Sobolev spaces. I'll define it a bit later. And let me mention something about stability results. As you see in the literature, there are many so-called conditional stability results for inverse problems. I'm afraid I have to be a bit critical here. Stability estimates usually consider two conductivities and their Dirichlet-Neumann maps. And they show that when the data, when these two data become close to each other, then these guys go close to each other. However, from a practical point of view, this is really not so relevant because these guys are now on the range here. And actually what we measure is this one. It's generally never on the range. I mean, it's with probability 0. I mean, it's just not on the range. This is our starting point, and analyzing what happens on this line here, while mathematically interesting and while giving very useful techniques for proofs, really is not yet the solution of the inverse problem. And let's see, so we would like to construct regularization strategies for all inverse problems. I think this would be the goal of the field, to have numerically implemented and mathematically proved regularization strategies for all inverse problems. So this is the set of all inverse problems, and let me discuss a little bit what is known about regularization of them. For linear inverse problems, I would say the situation is pretty well known after the work of Tikhonov and many, many others that I don't even attempt to list here. Then, to fill up the whole space of all inverse problems, I see kind of two different attack methods. One is to use Tikhonov regularization and generalize it outside linear ones. Assume some sort of nonlinearity and push the regularization outside the linear ones. There's a lot of work done in that field, and what is nice about these methods is that they are Tikhonov regularization type, so they apply to many. Once you program a method like this, you can apply it to many inverse problems, which is nice. There's a problem though. The assumptions currently known do not really cover many of the important very nonlinear problems like optical tomography, inverse scattering, ultrasound, inverse kinematic. So another approach would be to take one by one important problems and tailor a regularization strategy for them, specifically, problem specifically. That's not so general, which is of course a minus, but on the plus side, we will get a regularized inversion method. There are not so many of those so far. In EIT, there are a couple of works for finding inclusions, so not for the full problem of finding the whole coefficient. There's some work for blind deconvolution, and to my best knowledge, there is only one work dealing with the global PDE coefficient reconstruction, and that's the one I'm talking about today. So let's see how Nachman's two-dimensional proof works. That is the basis of the regularized method I'm talking about today. So Nachman starts by assuming two derivatives in the conductivity. Also, let's assume that the conductivity is 1 near the boundary. And of course, the conductivity is also bounded away from 0. It's strictly positive. With these assumptions, we can define this function Q by continuing sigma as 1 outside omega. Defining this one, here are two derivatives. Here we divide, but we don't divide by 0 because it's positive. So we can define this Q and continue it as 0 outside omega. And now we look at the Schrödinger equation in the full plane. We look for solutions of the Schrödinger equation parametrized by a complex number k, complex non-zero number k. We are interested in solutions psi that behave like e to the ikz. In this sense, if you multiply it by e to the minus ikz, we get something very close to the constant function 1. Not equal necessarily, but close in the sense that they are in this Sobolev space with p tilde greater than 2, so these are continuous functions by Sobolev embedding. And please notice that this e to the minus ikx contains this complex multiplication. So it's not unimodular, it's growing and decaying in some directions. These are the so-called complex geometric optic solutions. And let me discuss how to construct these guys. We define this mu function by this formula, so we kind of take away from psi the asymptotic growth, so we multiply it by this exponential, and plugging the result in this formula, we see that mu satisfies this kind of PDE. So there is a first order perturbation of the Laplace operator and the same Q here. And this d-bar operator is the usual complex analytic operator. So now we would like to find solutions to this partial differential equation with this asymptotic condition. The way to do it, as Nachman approached the construction, is to look at this Lippmann-Schwinger type equation. So this is not physical scattering, but this is kind of a mathematical, like Lippmann-Schwinger equation. So this is the incident wave, constant function 1. This is the Green's function, but it's the Green's function for this PDE here, defined, for example, by inverse Fourier transform in the sense of temperate distributions. So it's easy to see that if we have a solution of this Lippmann-Schwinger equation, then it will solve this one, just by applying this operator on both sides here. But how to solve that Lippmann-Schwinger equation? Oh, let's take a look at the fundamental solution, gk. So I just showed the g1 because we have this formula gkz equals g1 at kz. So it's enough to compute numerically this g1. This is something I did in my PhD thesis. find numerical formulas for this fundamental solution. Here's the real part. It has logarithmic singularity. This is the imaginary part. It is continuous and is 0 at the origin. Okay, the construction then, we would need to construct mu satisfying this one with this asymptotic behavior. The way Nachman did it is he defined mu minus 1 as this function here. Of course, it requires some technical work to see that this is possible. First of all, multiplication by q pointwise is a bounded linear operator from the Sobolev space to LP. Q is now actually in any LP. It's a continuous, compactly supported function. Then there is some analysis to see what does this convolution with this fundamental solution do. Well, it maps LP to this Sobolev space, and actually it's a compact operator. So this operator here is identity plus compact, and the invertibility here can be seen by a Fredholm argument. And this is one of the big breakthroughs in Nachman's paper. He could use the theory of pseudo-analytic functions to show that this operator is injective. That it means that these complex geometric optic solutions uniquely exist for any k, any parameter k non-zero in the complex plane. And let's see one of the properties of these mu functions. This is, I'm really hand-waving here and omitting a lot of technical details, but just bear with me. Let's put k to 0 in this formula. This will disappear. We get 0 here, and q equals this guy by definition. So this mu z of 0 satisfies this equation, and if we look at this asymptotic condition, actually square root of sigma is the one that satisfies it, because we continued it as 1 outside omega. So this gives actually the last step of the reconstruction. We will get the conductivity or square root of conductivity back if we find this function. And now the main ingredient in the proof, I would say, is the so-called scattering transform, also called the nonlinear Fourier transform. So we define it in this way. If we know q, we define the scattering transform like this. It's integration over the plane. We have q here, psi here, and some exponential function here. Now, if psi would be equal to I to the ikz, in that case, this integral would equal this one. And after some computation, we see that actually it's the Fourier transform of q evaluated at this point. However, psi is really not equal to this one. It's only asymptotically close to it, and it depends on q. That's why this t guy here is nonlinear in q. Q is here, and also this one depends on q. But it's somehow close to the Fourier transform anyway. So this is the crucial object, and bear in mind, it's just a function from the complex plane to the complex plane, defined in this way. And now how to use it for electrical impedance imaging. This is, Nachman showed that the traces of the complex geometric optic solutions satisfy a boundary integral equation like this. So this is something explicit, restriction of this guy to the boundary. Here we have the measurement data. This is the measurement data for homogeneous conductivity 1. We just assume we know it, although it's not always obvious, but let's just assume for the sake of the argument that we know it. So this we measure, this we know. This is the single layer operator defined like this, but the Green's function here is not the usual logarithmic type. It's a Fadeev-Green's function defined in this way, but nevertheless it is a Green's function for the Laplace operator. So there is this Fredholm integral equation of the second kind. Here is identity, here is something compact, and actually I think the difference here is compact. So Nachman showed that also this one can be solved uniquely, then the result can be inserted here in this kind of integral where we use the data another time. Where these formulas come from is actually using Alessandrini's identity, which is a version of the Green's theorem. So starting from the boundary measurements, we find the traces, put them here, use the measurement another time, and miraculously we know this nonlinear Fourier transform of Q from the measurements. Then, let me just show you. This is the usual Green's function for the Laplace operator, and this is the Faddeev Green's function. So the difference is a global harmonic function depending on k. This is just for k equals 1. So how to use this scattering transform then? Now we face the second step of the inversion from the scattering transform to the conductivity. This is actually a well-posed step. What is ill-posed is the going from boundary measurements to the scattering transform. The ill-posedness of EIT is kind of hidden in that part. So now what happens here is that if we think about, okay, we have these solutions that they exist uniquely and they depend on a complex parameter k. So then we might ask, is the dependence analytic in k? So let's test it. Let's hit the functions with this d bar operator. If this gives 0, they are analytic. It's like the Cauchy-Riemann equations. What happens when we hit this guy by this operator? If you look at the Lippmann-Schwinger type equation, what happens actually is that the derivative of this operator is a rank 1 operator containing the Fourier transform. And what happens is actually we get something non-zero on the right-hand side and including mu itself. This is quite a non-trivial formula, and it was originally found by Beals and Koifman in the context of nonlinear evolution equations, like the Davis-Stewartson equation. And it's quite a remarkable formula, I would say. I don't know how to develop intuition for this one. I haven't, although I've been working with this for 15 years already. I don't know if there is intuition for it. Okay, but anyway, let me summarize Nachmann's proof. So, given the boundary measurements, first solve this boundary integral equation for every k, well, excluding 0, but otherwise every k. Compute the scattering transform for, let's say, every k non-zero, but we know actually theoretically that this guy goes to 0 at 0, so we can just substitute t0 equals 0. Then we know the scattering transform, we put it here, and we solve this d-bar equation with such asymptotic condition. It can be done, for example, by passing to an integral formulation of this equation, as we will see, and then we get perfect reconstruction of the conductivity by squaring the solution when k is 0. So this is the infinite precision recovery of the conductivity. But in practice, we cannot do it. We have to introduce an extra step. So let's see what kind of extra step. Let me start with a numerical example. Let's construct a C2 conductivity looking like this. So these are kind of lungs with low conductivity because there are air in the lungs, and this is kind of the heart filled with blood, and then it's more conductive. So this is another view of the same function. So let's simulate data from this one and try to reconstruct. Well, a bit later, let's first see how the scattering transform looks like. So here I cheated and I know the conductivity and just use all the definitions and numerical computation of the CGO solutions to compute the nonlinear Fourier transform. This is how it looks like in the disk when k is in the disk of radius 10. So this is the real part, the imaginary part of the conductivity, the scattering transform of the conductivity we just saw. So this is computed by cheating, but when we start from the actual boundary measurements, this is what happens. We can compute near the origin with high quality, but then at some point the computation breaks down. And the reason is that there is, even if there's only small amount of noise in the measurements, it will get multiplied by functions behaving like e to the ikz. And when k grows, we are taking k away from the origin. At some point, the errors get multiplied by exponentially big numbers and everything breaks down. But as you see, if I go back and forth between these pictures, you see in the middle, it's quite okay. I mean, we have some reliable results here. So this is why we came up with the idea of just truncating. Just take whatever is inside here, outside put it to 0, and then compute And this is really what this nonlinear low-pass filtering is. So here you see what we saw already, Nachmann's infinite precision data reconstruction, and here is our practical reconstruction. So we start with the noisy data. We plug it here in the same equation than this one. Of course, now it's unclear, can we solve this or not? But we proved that it can be solved within when k is in some disk of radius r. I will give you the radius r specifically or explicitly. So we solve this for a disk. Then inside the disk we evaluate the truncated and noisy scattering transform by the same formula, but using these noisy things here. And outside the cutoff frequency, we just put it to 0. Then the d-bar equation is essentially the same. We just have here the truncated coefficient in the PDE, which actually makes it easier to solve it numerically. And we use this. We solve this one with this asymptotic requirement, and then we define our regularization strategy by the square of the solution of this equation evaluated when k is 0.
Sorry, can I ask a quick question?
Yes.
You hinted early on of stability estimates not taking account that the data might not be in the range.
Yes.
Somehow here, have you projected onto the range
No.
somehow? No,
We cannot project because we don't know. The range is not characterized.
But this all works fine for something that's
This
not
can
in
be
the
any,
range.
it can be any operator just at most delta away from the,
Okay.
yeah. And you'll see the precise definitions in a minute. So now, there was the question, what are the data space, model space and data space? So our model space is L infinity of omega, and the domain of the forward map is defined like this. We have two pieces of a priori information, m and a radius rho. So the C2 norm of sigma is bounded by m. Sigma is bounded away from 0 by 1 over m. And in a neighborhood of the boundary, sigma equals 1. This we know a priori, and this is the definition of the domain of the forward map. Then the data space, it is a subspace of the space of linear operators between these Sobolev spaces. The Dirichlet-Neumann map is known to map between these spaces. And we just have these two extra things that we know that actual Dirichlet-Neumann maps always satisfy. Applied to a constant function gives 0, because then the solution is just constant. And the normal derivative is also is 0. And by conservation of charge, we know that these always integrate to 0. So these we can easily enforce in measured data. So our measured data belongs to the data space. Now we have a theorem. First we start with a small constant. So this is only for small delta first. So there is a delta 0 such that if the error in the data is less than delta and delta is smaller than this delta 0, then we can choose the cutoff frequency in the low-pass filtering by this explicit formula. Please notice that there is no mention of the a priori information or anything. It's just an explicit formula like this. And we define the regularization parameter by 1 over the cutoff frequency. This way, the theorem states we get a well-defined regularization strategy that not only goes to the error goes to 0 when the noise level goes to 0. Additionally, we can give an explicit convergence rate in a Banach space. So let's see, why would such a thing hold? The proof is based on several lemmas. First of all, let's take a look at the integral formulation of the d-bar equation. So here actually is convolution with the fundamental solution of the d-bar operator, which is 1 over pi k. And we are solving these equations with different kinds of scattering transforms here. So if we have two guys, phi1 and phi2, and the solutions mu1 and mu2, then the solutions in Hölder continuity norm are this close to each other, bounded by the difference of these kernels here. And we have some explicit or some knowledge about these exponents. This is mostly using Vekua's results from the 60s about pseudo-analytic functions. Then we have some new estimates on Fadeev-Green's function that provide us with these estimates. So the single-layer operator with this k parameter is less than this one. Of course, this is something very large in k, but nevertheless, this is good for our purposes. And also, this inverse operator we need when solving the boundary integral equation is bounded by this bound. And these c constants here depend on the a priori information. Then we prove that this boundary integral equation can be solved for delta small enough, because we know that without the delta, by Nachman we know it's solvable for a given sigma, and then with small delta we are not too far away, and we have these estimates, so we can prove that this can be solved provided k stays within this disk with this explicit radius. Then also for the resulting truncated scattering transform, if we compare this one to the actual official scattering transform, we see that they are not too far away from each other. The difference is bounded in LP norm by this kind of. For any p more than 1, we have, and p also appears here. Okay, now what we should do to prove our claim. First of all, from infinite precision data, we get perfect reconstruction when alpha goes to 0. This is actually roughly Nachman's original result. We need lemma 1 and then going through Nachman's proof with very carefully choosing all the LP spaces there. This one is quite trivial because it's just by definition what happens. Alpha goes to 0 when noise level goes to 0. And then we should show that this reconstruction error, the supremum, goes to 0 when the noise level approaches 0. And for that, we use our lemmas. Remember that the final reconstruction was this guy with 0 here and square. That would be the reconstruction. And the actual conductivity is putting 0 here and square. So these guys are not too far from each other because we know that we have the Hölder continuity norm here. Then we can compare the two kernels in the D-bar equation, but we know something about their difference. This is inside the disk, and outside the disk we have only this one because it's truncated. And then these lemmas we just saw, plugging everything in, shows that we can bound everything with these kind of things containing logarithms and some powers, and we end up with this power 1 over 14, which is not optimal. It's just one of the exponents that work in this formula. So now with that proof we can show the result for small enough noise levels, which is not really satisfactory because, like I said, the range of the forward map is not characterized, so we don't know when we are close to it and when not. But fortunately, using a spectral theoretic extra step, we can actually define our regularization strategy on the whole of the data space Y. And then it restricts close to the range. It will restrict to the one we saw. And to my best knowledge, this is really the first time when a nonlinear inverse problem is regularized in this way. And then let's see how this works in practice. So what we do in practice is that, of course, we measure our data using electrodes and some current patterns. Usually currents are applied and voltage is measured, and several different current patterns are used. These are examples of so-called trigonometric patterns. So what we do is we take the kind of discrete Neumann to Dirichlet map, then we identify this kind of discrete functions with these kinds of trigonometric functions at the boundary, make an approximation there, get the Neumann to Dirichlet map in a continuous setting as a finite matrix in a basis given by a finite collection of these functions. Then we invert the Neumann to Dirichlet map to get the Dirichlet to Neumann map, and then we can start solving this equation numerically. We just write every linear operator here as a matrix in this finite basis, and then we just invert the matrix. And this seems to work fine in a disk in the K space, and outside the disk it fails miserably. That's just what happens. Then once we get the truncated scattering transform from the previous step, we should solve this d-bar equation. And what we do, we follow Gennady Vainikko, who invented a nice method for solving Lippmann-Schwinger equations based on periodization and FFT and GMRS, which are quite powerful techniques all. So what we do first, we convolve both sides here by 1 over pk, which is the fundamental solution for this guy. So what is left on this side is mu itself. Here we could actually plug whatever analytic function we want. However, we want to achieve this asymptotic behavior, so we put the analytic function 1 here. And then here we have the convolution of 1 over pi k with this here. So we want to solve this Fredholm integral equation, and what we do is we make use of the truncation here. We take the disk of radius r, and actually we take the disk of radius 2r and a square that is a little bigger and contains this bigger disk here. In this square, we tile the whole plane with these squares and consider periodic functions. And now, because in this convolution, the maximum size of this guy is 2r, because this is actually only an integral over the disk of radius r, because this is supported there. So what happens, a periodic version of this equation gives the same solution than the full plane equation inside the smaller disk. Outside they do not coincide, but inside they do. And now if we solve the periodic equation and get the solution, we just plug it here. It's only used inside the disk of radius r because of the truncation, and then we get the actual full plane solution everywhere from the left hand side. And how to solve this in the periodic setting? We take this grid you see here, actually a bit finer in practice, but this is a grid that has 2 to the m points by 2 to the m, and it's exactly a grid that goes fine with fast Fourier transform. So then essentially we feed GMRS or other iterative linear equation solver this kind of algorithm that, starting with any function phi, which is given at the grid points, it multiplies the function pointwise with the function that appears in the d-bar equation, complex conjugates. Then here is the Green's function. At the origin we just put 0 here because it's singular, and in other places we just put this 1 over pi k in the grid points. Then we take FFT, multiply inverse FFT. This takes care of the convolution, and then we just subtract. So this is the way to implement phi minus 1 over pi k convolution multiplication of phi in a nice way, keeping the real and imaginary parts separate, because this is a not complex linear operation here. So we actually represent functions as vectors, where first the real parts of all of these guys and then the imaginary parts of all of these guys. Then we write up a MATLAB file that does all of this here using FFT. We feed that to GMRS and we get the solution. And let's see some results here now. I computed for the conductivity phantom I showed you some slides ago, the heart and lungs phantom, I computed the Dirichlet's Neumann map numerically using the finite element method, and the accuracy of my computation in the data space norm was roughly 10 to the minus 6. And then I added noise controlling the size of noise to simulate boundary measurements at different noise levels. And now here you see these truncation radii. And what I did here is I cheated a little bit. Let me explain. These black things you see here, this is where the computation of scattering transform breaks down. So I cheated and computed the real scattering transform. Then I computed the scattering transform honestly from boundary measurements. I compared them, and these black lines you see here, they show when the computation breaks down. I think when it's more than 10% error point-wise. Then I just pushed this red cutoff frequency as big as possible while staying in this relatively high quality computation. And computed for you the reconstructions. You see this is the reconstruction relative error in the reconstruction. So when the data is more noisy, of course, we start to get worse and worse reconstructions. And the effect is kind of a low-pass filtering, although it's actually a nonlinear effect, but still. And now, if we look at this my cheating, so here I plotted these red radii as the function of noise level. So here the noise level, this is a logarithmic scale, so noise level is becoming smaller. Here are the experimentally found maximal cutoff radii. Here is the thing predicted by theory. This is shown here. So actually in practice, whatever we choose in here, this between, would give us stable regularized reconstructions. And this is not so good. If we see this is, even in this case, this would give something like 1.5. And if we look at even with 2.5, we get quite bad reconstruction. So I would say that this prediction by theory is way too pessimistic. So actually, we can take much bigger radii, and we should, because this will not give good reconstructions yet. So it's kind of a nice thing that the method works even better than predicted by the theory. But anyway, this is something that we surely can do, and everything is regularized properly. So to conclude, I would say that we have here the first non-iterative direct regularization method for a full nonlinear global PDE coefficient recovery problem. It works in practice. Here is one example when we apply it to real measured data. It can also be applied to human data. We are in the process of doing it. We have done it with some Born approximation step and got really nice videos of people's breathing. So I would say that here is an instance where numerical complex geometric optic solutions can help medical imaging.
Just coming back to the range question, it occurs to me that, of course, in the end, you're measuring some finite dimensional data space because you're using electrodes.
Yes.
And there is a range characterization for the 2D finite dimensional.
Mm-hmm. Oh, there is?
You know,
is there? I haven't seen that.
I think it's a paper by Morrow and one of his collaborators based that comes out of the resistor network theory, but it's a continuum range characterization. So I'm not sure that helps, but it occurs to me that also that by your truncation in the Fourier transform space, it seems to me you have a finite dimensional manifold of solutions, because they're the Fourier truncated ones. I know it's non-linear, but I think it's a finite dimensional manifold. So there's kind of another aspect here that that's not coming out. That there's also the finite dimensional approximation as well as the error regularization. So. I think somehow the projection onto the range might have happened in the finite dimensional data space. You know,
when we add the random noise there, I'm afraid that it goes out. It could be projected, though, I guess, if there is like characterization. But I don't think.
I think it's the same criteria for resistor networks. In which case it's easy to characterize the range.
Yeah, then
so you could project onto the range.
Yes. And that would be another way to regularize. Then use a stability result. And then, could be, yes.
But a question, so when you solve your interval equation of the boundary, then you also said that the difference of this derivative phenomenon operators is a probably compact. Actually, I assume it will be much better for this Schatten class space. And there is in scattering theory this nice theory of the Maschwinger saying that if you have some information about trace norm or Schatten norm or some difference of, well, in his case resolvent operators, but it works the same way also for derivative phenomenon operators, then you can see something about the long-time behavior of scattering problem. Do you have something like that?
Sounds very interesting. I don't think we have something like that. But definitely, I mean, in this case, especially when the conductivity is 1 near the boundary, then the difference between those maps, it's an infinitely smoothing pseudo-differential operator, so it's as well behaved as an operator can be, I would say. So yeah, that would be interesting to look at. Thanks. Yes.
What happens if the conductivity is not smooth? Could you still reconstruct the conductivity?
Yes, it actually the whole thing goes through. That's kind of interesting. The boundary integral equation is still solvable. I think it follows from the Astala-Päivärinta theory actually that the boundary integral equation can be solved. And then we can plug the scattering transform in, truncate in the same way, and we get quite useful pictures. Let me show you. These are pictures we get from implementing the Astala-Päivärinta approach. And actually, when we use the exactly same data and put it through the Nachman method, we get extremely closely the same pictures. This is currently slightly puzzling because there seems to be some theoretical reasons that they really cannot be the same thing. But numerically, at least with these truncation radii, they give exactly the same thing. So I would say yes, with discontinuous targets like this, we get an image like this, and also it works for real measured data, so which is also discontinuous. So there are some hidden secrets still in this field to understand what's going on in that case.
And what happens if in medical imaging you have sources and receivers all around the body, but in let's say in Earth to image the Earth with electrical currents, you just have sources and receiver at the boundary at the top, let's say.
Yes.
So how would the result be great?
That's a very good question. I think a logical next step would be to move to a three-dimensional setting and use a partial measurement. The problem is that the key element here is Nachman's proof that these CGO solutions exist uniquely for all the parameters k. In 3D, this is an open question, whether the solutions are unique or not. So far that has prevented progress in that direction, I would say.
You can try. Why not?
That's a good idea.
Not some theorem, just try.
That's right, that's a very good idea. We are actually in the process of doing it. It's technically a bit involved, but
it seems to me that what you prove now, show you now, that it's not good idea to try to get very high accuracy in results, because it is logarithmic or something delta power 1/10 and something like this. It is practically not small thing. So
yes.
Forget about the high accuracy. Forget about the theorem, because the theorem is logarithmic quality. Forget about that. Just try. And there is a very interesting situation that when you try to take that measurement, the delta, the arrow, in some interval, so you get good result. If you try to get outside this interval, you just drop out completely. So it's necessary to understand what is the reason. What is the reason? So something which is practically good, and after that just practically bad. What's going on here? It's interesting to understand, first of all. The second, maybe also things. You try to cut off this data in K domain by means of the ball, some sphere. But wait, it seems to me that it is not symmetric with respect to imagery and positive or not. Is this correct? Because when you try to construct this function, it is something which is increase exponentially or decrease exponentially. It seems to me that it is not symmetric with respect to reflection.
I think you're right, yes. So
maybe it's a good idea to use not a ball, but something not unique, but maybe some other
Yes.
domains.
Yeah, I agree. Probably it would be an improvement.
Sorry if this is not a pertinent question, but your definition on noise, I think it's an unfair question. Compared to the real sources of noise in a massively discretized version of it, how does that play out?
Yes, that's.
I know it's sort of outside the mathematics of it.
Not really, because there would be a natural next step in this analysis. If you look at the work by Armin Lechleiter with the factorization method and the regularization analysis for it, he uses actually Nuutti Hyvönen's analysis, what happens in EIT when the number of electrodes is increased and the measurement precision at each electrode is increased. This is kind of more natural thing than say that delta goes to zero. The more.
But when you say that you're in massively discretized version of the real model.
So I think the correct thing to look at would be in the same way that Hyvönen is doing, to increase number of electrodes, decrease or make the measurement more precise, and actually that would be much more correct way of looking at the measurement error.
Okay.
So and I think it probably could be combined with this analysis, just not done so far.
This exactly. He proves that it is not necessary to prove this noise is very, very small.
Yeah. But what if I want to see more than a couple of blobs?
Forget about the noise. This is.
Yeah, I think for seeing more than a couple of blobs, I think that's very difficult because it's really not enough just to use more electrodes.
Yeah.
It's theoretically understood that at the same time you have to exponentially increase the measurement precision. So you should also have significant numbers.
Well, that simply can't be true because fish, weakly electric fish, have hundreds of electrodes all over their body, and I doubt if their precision is more than 12 bits. There must be something you can do with that data.
Could be.
I mean, evolution isn't wasteful in that way.
That's right. Yeah. Yeah, I think the really interesting points. I mean, this would be good to understand better. Yes.
And here you did the 2D experiments. So the harmonic functions are in log of r, log of the distance in 2D, but in 3D they are in 1 over the distance. So my question is that you have a circle or a zone where you have a valid result, and outside of the zone then the result is not valid anymore. If you would do it in 3D,
yes,
would that valid zone be larger or smaller, or what do you think?
good question. I mean, the thing is that these solutions are like e to the I zeta dot x, where now x is in Rn and zeta is in Cn. In what I was talking about, zeta, and here, yeah, zeta dot zeta is 0. So in 2D case, these can be parameterized in this way. So this is the k I was using, and this is the zeta it corresponds to. Now in 3D, the parameterization is not this simple. It's more complicated. But I think anyway, it would be some kind of, in the same way, it could be some kind of a ball in the C space, a ball, and inside the ball the variety defined by this. Somehow I don't know how it looks like, but I would say the shape is quite different, but the radius I think should behave roughly in the same way, because anyway the error comes from the measurement error being multiplied by such an exponentially large function when zeta grows. So I think that's the where the errors come from, especially because the error is in the point is that when solving this equation, the error is not in the right hand side as usual. This is perfectly known, but the error is in the operator, so it's inside here, which makes it kind of funny when we write the inverse operator. I think that's why it just breaks down suddenly, because this is a Fredholm operator, and when we make delta bigger, it gets multiplied with numbers that are exponentially big in k. And this is the same thing that happens also in 3D if you look at this similar equation.
So here you split into two parts, and the first part is just to get rid of the infinite amplitudes that you would have at the source.
Sorry?
So in electrical
Mhm.
conductivity, you have an infinite amplitude at the source. So most of the time you split into two different potentials, a reference
Mhm.
potential and an addition potential. Is it there or
In here?
yeah, or is it in a different?
No, we divide it. Yeah, we actually write it as a sum of the usual singular operator and something a smooth integral operator. So I guess yeah, that's what we do.
If there are no more questions, I should suggest we thank the speaker again.